Okay, so now we'll actually do ANNOVA, that is actually analysis of variance, right? So this is another statistical test, right, which we'll actually do in our research problems, right, and it's highly employed in the research papers for the statistical when they want to actually know that you actually what's the statistical significance of your study and while doing hypothesis testing and all. So you actually asked to do the ANOVA test and tell the results so that you can signify whatever you are suggesting is statistically significant. Okay, so ANOVA stands for analysis of variance, and this is a technique is used when multiple samples are introduced. Okay, are involved or introduced, whatever, right? So you have different multiple sample cases, right? And you have multiple ones are actually involved in the particular study. Then you actually use this particular test, that is ANOVA. And ANOVA is used to examine the significance of the difference among the more than two sample means uh, uh, less in time. Using ANOVA, one can draw inferences about whether the samples have been drawn from the population having the same mean. One quite often utilizes the ANOVA technique through its investigation the differences among the means of the population simultaneously. The essence of ANOVA is that the total amount of variation in a set of data is broken down into two types. That amount which can be attributed to the chance, and that amount which can be attributed to the specific cases. There may be variation between the samples and also contain the sample items. Another technique, uh, Another technique, one can investigate any number of ways which are hypothesized said to influence the dependent variable. If we take only one factor and investigate the differences among its various categories having numerous possible values, we said to use one way ANOVA. So basically, it's actually kind of a test which actually used to test whether there are particular two means in the particular distribution when we have. Basically, there are particular different categories or different clusters into the particular sample, and you are drawing out from say multiple samples, right? You are drawing on multiple samples and the results are coming out to be say different. So it actually tests that whether this is by chance or say you are actually getting the results in a significant manner, and there are essentially two particular clusters or say two particular means among the population. There are particular two types of ANOVA test, that is one way ANOVA and two way ANOVA, right? And we'll actually better understand with the examples, right? Okay, so uh, further, in the case we investigate the two factors at the same time, then we use the two-way ANOVA. So when we actually consider only one factor, then we consider the one-way ANOVA. Otherwise, if we actually consider two factors, then we used to use two-way ANOVA. Now, basic principles of ANOVA is to test for the differences among the means of the population by examining the amount of variation within, right? So what are the means of the population means? What are the multiple means of the population? We used to calculate the variation among our data samples, and we actually get the inference about the means accordingly. Okay. In terms of the variation within the given population, the sample, it is assumed that the observation alpha ij differ from the mean of this population only because of the random effect. Whereas in examining the difference between population, we assume that the difference mean of the jth population and grand mean is attributed to what is called a specific factor, or what is technically described as a treatment effect. While using ANOVA, we assume that each of the sample is drawn from a normal population and that each of the population has the same variance. Okay, so you are actually just assuming for the ANOVA that your sample is actually having a normal distribution, right? And the variance, while the means are actually different, but the variance among the different population is actually same. The variance sum is actually same, and this is actually an assumption for the ANOVA. We also assume that all the factors other than the one or more being tested are effectively controlled. The total variance in a point sample is partitioned into two parts: between the sample variance and within the sample variance, right? The total variance means for a point sample is partition. The total variance is actually a combination of these one. first one is actually the between sample variance, and the second one is actually the within sample variance. Means in a particular sample you are calculating the variance, and between two particular samples you are calculating the variance. So there are two factors of variance, total variance calculation in ANNOVA. Between sample variance is due to the different treatment, while within sample variance is due to the random and unexplained disturbance, right? So between sample variance is nice, right? Because you are actually calculating the variance among the different particular sets, right? But in a single sample there is a variance, right? So this is actually due to the random and unexplained disturbances, right? Which must not be there, because if it's actually a single sample, then there must be no variance in it, right? There must be very less variance, because this is actually coming out from the same distribution. Now test the statistic FC, that is between sample variance by within sample variance. So you are actually having a test statistic, right? That is FC, right? So what is the formula here? That is actually whatever your between sample variance is coming out, and divided by what is the within sample variance is that. So within sample variance is actually between the same sample, and between means among the different samples. So you actually calculate the test statistic, and C means computed as previous scenarios also. Now we wish to test the hypothesis H0. As we have already discussed, we have two types of hypothesis: null hypothesis and alternative hypothesis. So in this case, in this particular example, we say that all the population means are same, and H1 says that all the population means are not same, right? The population means are same means that all the sample population which you are drawing are actually having the same value, right? But H1 says that all the population means are actually not same. So our null hypothesis must be true, and it will be true according to the value of this FC and the critical value which is observed from the tables. Between sample variance is large when effect of all the treatments are different. Okay. In such case, FC is large and we are likely to reject H0. So the test is right-tailed test, right? We have also discussed a bit about say left-tailed test or right-tailed test, right? Right-tailed test is actually the one when we have the rejection region towards the right, and the left-tailed test is actually the one where we have the rejection region towards the left on the normal distribution, right? So between sample variance is large when the effect of all the treatment is different, right? Means when you actually do some sort of treatments over the population, and the effect of them is actually very large. So that's why you have the between sample variance coming out to be very large, right? In such case, then FC will be also large, and because the between sample variance is all over the top right, and that's why FC will actually coming out to be large, and in this case we will reject the upper null hypothesis. So this is the condition when we are actually having our FC to be very large value, so likely we will reject this, and it is considered a right tail test here, not the left one. So we used to have different tables for the right tail test and the left tail test also. So we'll actually consider right tail test table for this case. So let's actually see when we have one factor in the consideration, that is one way ANNOVA, right? Okay. So obtain, what are the multiple steps of this one way ANNOVA? That is obtain the mean of each sample, right? That is x1 bar, x2 bar, and xk bar. So these are the mean of each sample, right? Means we have k particular samples, right? And we have calculated the mean of each of those samples. Now mean of the sample means, now we also need to calculate all the mean of all of these ones, right? Mean of all of these samples, right? Means of the means is actually x bar. So that means that you will actually calculate x1 bar, x2 bar, and xk bar, and add all of them and divide by k. That's actually your say mean of the sample means. You will need to calculate this also. So now you will actually find the sum of squares between this is actually the third step, that is you actually find the sum of squared. How you will actually do that? We'll actually do say n1 multiplied by x1 minus x bar, x double bar whole square, plus n2 multiplied by x2 minus x2 x double bar whole square, and up to nk and xk bar minus x double bar whole square. So n must be the number of samples in that particular sample, right? Means in the first sample we have say n1 number of samples, and in the second sample we have say n2 number of examples, and so on, and that's actually being multiplied by the x1 bar minus x double bar. So this is essentially calculating the variance, right? Variance between the particular sample means how are the means deviating among the different samples taken for a particular population, right? Now we'll actually calculate the mean squared. This was the sum of square, and this is the mean squared. So variance also need to be in the variance calculation. You must have observed that there is a divide term by the number of samples, right? So here we are doing the same. First you just multiply all of these things and then divide by k minus 1, right? So k minus 1 is nothing but the degree of freedom, right? So k is actually the number of samples, and we actually divide by k minus 1 as the degree of freedom. Now s is between is actually s is within is actually sum up from 1 to n, and then okay, so s is, now it was the s is between because we were considering multiple samples, right? In between samples we were actually calculating the between thing, right? But now we'll actually calculate the within thing, right? Because the FC statistic was that in the previous slide also, it was that between the samples variance and within the sample variance, right? That's actually a FC statistics. So basically here you are calculating the between sample variance through this formula, that is ms between, or mean square between, right? And then ss within will be actually calculated by this particular formula, right? So what is this? You are summing over 1 to n, and then you are doing x1 I minus x1 bar whole square plus summation over 2 I minus 2 bar whole square, and going up to say xki minus xk bar whole square, and then divide by n minus k, right? N minus k, this is the particular term, right? Okay, so what you are doing essentially is that say within one is actually being calculated in this fashion, that is okay, so what you are doing is that for each of the sample you are subtracting for, okay, so let's actually consider the first sample, and in the first sample only we are taking up all the examples, right? We are taking up all the examples. Here the talk was about just the particular mean of the sample and the mean among the different samples, but here the talk is about the all of the samples in a particular sample, and we are just subtracting the particular mean term of that particular sample from each example's value, right? That's actually what we are doing, right? So essentially, for example, we have say 10 samples in sample 1, 10 samples in sample 2. So what we are doing is that we are calculating the mean of this sample 1. We are just subtracting every mean from every of the value, and then we are squaring up everything and we're summing up. Then we are doing for the second sample, that is mean of the second sample subtracted from the second value, second sample's first value, second value, and so on, and we are squaring up and so on till the kth particular sample. We calculate the mean of the kth sample, and then we are subtracting from the each of the examples the kth mean value, and we are adding up all of those, and we are actually getting the ss within value. This is actually sum of the squared within value. And then for the mean for the mean squared, we actually need to divide by some of the factors. So how many total samples are there, right? How many total samples are there? Total samples are actually n, because see, n1 was actually the sample in the number of samples in the sample 1, number of examples in the sample 1, but n is the total number of samples, right? Now we need to also divide the k factor, that is actually the number of classes in the denominator, because this term actually includes all the samples, right? So we will actually divide by the k n minus k instead of just n. Now ss for total variance is equal to ss between plus ss within, right? So total variance will have two factors as we have studied, that is ss between and ss within, and the f ratio or the f statistics will actually come out to be say ms between by ms within, right? So ms between we actually got already with this particular formula, and ss within we actually got from this particular formula. So we sorry, ms within we actually got from this particular formula, right? And we divide that, we'll actually get the f ratio, that is, or the fc statistic. Now we have the f distribution within k minus 1. Okay, so what is the degree of freedom? We also need to get the calculate the critical value, right? So we'll actually calculate the critical value with the k minus 1. Okay, so that's actually your you will have two values here, right? In the earlier terms, you used to have only single thing for the degree of freedom, but now you will have two things for the degree of freedom. One is actually k minus 1. K is actually the number of samples you have taken. So k minus 1 is actually your first element of the pair while looking into the table in the column section. And then n minus k is actually your second degree of freedom, because this is the second thing which you are calculating. So you will actually also see the n minus k value in the table, right? In the left hand side, you will always look like the significance level, whatever the value is. So we'll actually get the F distribution value by looking at the table, and by comparing this value, which is F ratio, which is calculated, and the F distribution, which is looked from the table, which you actually look from the table, you will actually get to know whether to reject the null hypothesis or to accept the null hypothesis. Okay, so now you have the sources of variation, right? Okay, so these are the all formulas, right? What we have described in the same fashion. We have just a formula. So these are the sorts of variation, means from where the variation arises. So between sample or within sample, right? Or the total one, right? So sum of squared SS between and SS within, and then you have say mean squared, that is MS between and MS within. I believe that this table will confuse you a little more. Rather than this, we have this general explanation to be very nicer, right? Instead of that. So still we must understand this, right? So the degree of freedom we know that is between the particular sample is actually just k minus 1, because they are k samples, so we have k minus 1 degree of freedom. We generally used to subtract 1 from that. Then we, within the sample, that is S is within a particular sample only, means you were adding all of those terms, differences term, then the degree of freedom is actually n minus k. And the total degree of freedom comes out to be, say, total samples minus 1, right? Because this is actually the general convention. You have the total samples to be, say, n, you subtract 1 from that, and you actually get the degree of freedom. So this is actually the sum of squares. So sum of squared is actually just xij minus x bar bars whole square. This is actually the total sum of squares, but I believe this is actually not usable. Then you have the ms between value to be coming out to be, say, ss between, whatever the value which we have seen. Let's revise. The ss between was nothing but the number of samples in the sample 1 multiplied by so number of examples in the sample 1 multiplied by whatever the mean of that particular sample was, subtract the mean of all the samples, and then square them up. Similarly, do for all of those, and you will get SS between divided by k minus 1, ms between. For getting the SS within, just subtract the mean of the sample 1 from every of the samples, square everything up, just add in the similar fashion for all samples, divide by n minus k. This is your ms between. Total variances actually add up those. Or one of those, but the f set is actually between by within. So here you actually get the formula, that is ms within by ms between. This is actually f ratio. Okay, so now the question actually came for the thing, right, which we have discussed. So you have the plot of land, that is 1 2 3 4 are actually the plot of land. Means what are the plot of land says, that is you have 4 plot of lands, right? Per acre production data, that is variety of wheat, right? You have 3 varieties of wheat, that's actually A, B and C. So now you have the production data, right? Means per acre production, right? That is for A in the land 1, means for the A in the land 1 you have 6. You have for the B in the land 1 you have 5. For C in the land 1 you have 5. So this is your production, right? So what you are actually having is that 3 varieties and 4 plot of lands, right? Now set of analysis for the variance is given for 3 variety of wheat. We know that for 4 plots, right? Set if the variety differences are significant, means in the 4 plot of lands are the variety differences very significant. Let's see, all the wheat varieties are same. Second one is that all the wheat varieties are not same. Means you want to know that whether all the wheat varieties are actually coming out to be same in all plot of land. And that's actually our null hypothesis, and the alternative hypothesis is that the opposite of it, that is all the wheat varieties are coming out to be different. So let's actually calculate follow our steps. So first we will actually calculate the mean, right? Mean of sample 1. So sample 1 is actually nothing but say x1 bar, right? X1 bar. So x1 bar is actually the variety. So you are actually getting the sample of say are actually of the variety 1, variety A, variety B, variety C, and so on, if anyone was there, right? You will actually not do along the row, right? Because you will actually get this intuition from the question only, right? The question says that state if the variety differences are significant. So you want to calculate the difference in among the varieties and not among the plots, right? So your sample is actually of A, B and C. So you have three samples, right? Three samples, not four samples. You're actually having three samples, right? Means one for this wheat A, another for wheat B, and the third for wheat C, because all are wheats, right? But we are actually just getting the samples of three samples of wheats, right? So we are actually required to calculate the differences in the varieties of these wheats, right? So that's why while getting the average, you will get the average of A, average of B and average of C, and that's what we have done. That is x1 for all plot of lands divided by 4 is equal to 6, x2 that is all are added divided by 4 is actually 5, and x3 all added up divided by 4 is actually coming out to be 4. Then we will actually calculate the average of all of these wheat means, that is 6 plus 5 plus 4 divided by 3. That is actually average of all. Yeah, now you can, that is actually 15 by 3, that is actually coming out to be 5. Now you can easily calculate the SS between. So you know, in all there were 4 samples, right? And one is actually having 4 samples and 2 is actually having 4 samples. So 4 is being multiplied by that, 6 is the mean of the sample 1, so 5 is the mean of all the samples. So 6 minus 5 whole square and multiplied by 4. Similarly 4 is being multiplied, 5 minus 5 whole square plus 4 is being multiplied, 4 minus 5 whole square. You actually just add them all, that is actually 8. That's actually your SS between. In the similar fashion, you actually want to get the mean value, so you would divide by how many samples were there. There were 3 samples, right? So how many, sorry, yes, how many samples were there? So k samples were there, here 3 samples are there. So we actually got 3 minus 1, that's actually k value. So 8 by 3 minus 1, that's the a by divided by 4, that's actually 8 by divided by 2, that's actually 4. So 4 is the ms between. Now you want to actually calculate, so how many total examples were there, total examples in the all the samples were there, you already know. The total what, 4 plus 4 plus 4, that is 12, right? 4 plus 4 plus 4, so n value comes out to be say equals to 12, right? So that's why n value is actually coming out to be say 12. Now you have say f ratio, you need to calculate the f ratio, right? F statistic. So this is ms between, and you also need to calculate ms between, so you also need to calculate the ms within value, which has not been done here. You can calculate it very easily by using the formula. So what you will do easily, right? So you actually know the mean of this particular sample, right? You will know the mean of this particular sample, that is 6, 5 and 4. So what you will do is that you will actually use the same formula which we discussed, that test. For each of the sample you will do what, 6 minus what was the mean, that is 6. So 6 minus 6 whole square plus 7 minus 6 whole square plus 3 minus 6 whole square plus 8 minus 6 whole square, do add all of them, right? And then you will actually do the similar fashion for this. Its mean is 5, so 5 minus 5 whole square plus 5 minus 5 whole square plus 3 minus 5 whole square plus 7 minus 5 whole square. Similarly for this, add them all, right? That's actually your SS within. And then you will actually do what is divide by n minus k. N is actually 12, so 12 minus k is actually 3, so 12 minus 3 is actually 9. So you will actually divide this thing with the 9, and that's how you will actually get the ms within. So you actually calculated the ms between, that's actually coming out to be say 4, and you will actually get the ms within, will actually get another thing. So you will actually get the f statistic by dividing the between term, that is 4 divided by within term. In this fashion you will get the f statistics ratio as we described in this particular slide, right? You will get the f statistics ratio. Now you need to calculate the two parameters to look into the table for the f distribution critical value, right? So k here are actually 3 because the 3 samples were taken, so 3 minus 1 comes out to be 2, and then n minus k comes out to be say 12 minus 3, that's actually 9. So we'll actually look into the table of the value 2 comma 9 of the parameter 2 comma 9. So you actually got f 2 comma 9, that's actually coming out to be say 4.26, and this is actually the value from the table, and what you calculated f ratio is actually say 1.25, and you know that f 1.5 is very less than 4.26, and that's why you will accept the null hypothesis, right, that the varieties are all same. If that's actually coming out to be so very high, then you are likely to reject the null hypothesis and accept the alternative hypothesis, right. This was the thing when only one factor is considered. Now we'll actually also consider two factors. So we'll actually use the two-way ANNOVA, right. So two-way ANNOVA is as follows. That is, take the total of the observations in all the samples and call it T. Okay, so you will actually get the sum of all the observations in all the samples, and you will actually calculate, give it the name T. Then you will calculate the correlation factor, correction factor, that is T square divided by n. Whatever the sum of all the observation was there, you will actually divide that by n is actually the number of observations in all the sample. And the SS total will come out to be, say, in this particular scenario, the sum of sum of square total will come out to be, say, by this formula only, that is xi j whole square minus t square by n. That is actually a correction factor. So this is your SS total, means all the population individuals will be squared up and added up, and then you will subtract t square by n from that. Now take the total of the different columns and then obtain the square of each column. Take the total of different columns and then square each column, then obtain the square of each column, total, and divide such square values of such columns by the number of items in the concerning column, and take the total of the result. Finally, subtract the correction factor from the total to obtain the sum of squares of deviation for the variance for variance between the columns, and that's actually coming out to be, say, SS between columns. So there is SS total and SS between column thing. We will understand more with the example. So you got the SS between rows, you will actually get the SS between columns, and then you will actually also get the SS between rows. Then SS for the residual or error variance, that is total SS minus SS between columns minus SS between rows. What is the total sum of squared? You will subtract SS between columns from it and SS between rows from it. Now degree of freedom for the total variance is actually number of columns multiplied by number of rows minus 1. Degree of freedom for the total variance between the column is c minus 1. Degree of freedom for the variance between the rows is rho minus 1, and the degree of freedom for the residual variance is actually c minus 1 into r minus 1, right. So for the total variance is c into r minus 1, between columns c minus 1, between rows r minus 1, and for the residual variance is c minus 1 r minus 1, right. So this is the table concerning all the formulas, right. That is the source of variance, degree of freedom, mean squared error, and the F ratio, right. So between the column treatment, what we'll do is that we will just add up, we'll square all of the values in a particular column, right, and we'll actually divide, subtract the correction factor from it, right. Okay, we will square all of the values, right. Well, we will divide by the number of values in the particular column, right, and then we'll subtract the t square by n, right, t square by n, and t square is nothing but we have studied that t square by n is correction factor, and the sum of all the observations in all the samples is actually just the t, means just add all of those values which are giving to you. So that's actually t, and you square and divide by n. Then the degree of freedom is actually c minus 1, because this is the column, so the degree of freedom here comes out to be, say, c minus 1. So mean squared error comes out to be, say, SS between column and divided by c minus 1, right. And hmm, so SS between you already know from this particular formula, and then you will divide by c minus 1, right. And the F ratio for this particular case is actually coming out to be, say, MS between columns by MS residuals. Okay, so MS residuals you already know, you have calculated, and you will calculate in the particular example further. And then for the row treatment, what you will do is that for each jth are the columns and ith are the rows. For each of the rows, you will just add up all of the examples, right. For each the rows means for among the particular samples, right. You will actually just add up all of the values after squaring them up, that is ci whole square divided by n. I means the number of particular observations, or it's the number of samples, I believe, and then you will actually subtract the t square divided by n. The correction factor, or also degree of freedom here will be r minus 1, you will divide by that. to actually get the ms between, in this case of say rows, right? And the f ratio will be ms between the rows by ms residuals. Okay, so let's actually talk about the residuals, right? So the residual error is actually total sum of square, right? Total sum of square, whatever was coming, minus s's between columns minus s's between rows, sum of square between rows and sum of square between columns. You will subtract from the total sum of square, and then the degree of freedom for the residual should be r minus 1 into c minus 1, right? Means whatever your c value is, that you will actually do c minus 1 and r minus 1. And then whatever the sum of ss residual is actually there, you will actually divide it by r minus 1 multiplied by c minus 1. That is actually what you do, because whatever you actually calculated, you will divide that by the degree of freedom, right? Okay. And then the total, in the totality you will actually do all of the sum, right? Means square of all of the values, and then sum them up minus t square by n. T is actually just the sum of all the values. That's actually the sum of square of all the values, right? And then the degree of freedom here is c into r minus 1. That's actually talk of the total, but while talking of the residuals, we have c minus 1 into r minus 1. Now you have the MOC, right? HOC, the variety of the first factor have same effect. The varieties of the first factor are significantly different, right? So HOC says that the variety of the first factor have same effect, and HAC says that the varieties of the first factor are significantly different. Okay, then in the second thing you are talking about the HOR. The varieties of the second factor has the same effect, and the varieties of the second factor are significantly different in the similar fashion. So you have four things here: HOC, HOR, HAC, and HOR and HER. And you're calculating the first factor are different, same, and then for second factor same, and second factor different. That's why it is two-way ANNOVA. Now f column is actually ms between columns by ms residuals, right? So f column is actually coming out to be equal to ms between columns by ms residuals. Means f for the column is actually whatever the mean squared error value is actually before the between columns, divided by ms residuals, whatever the residual values. Okay, so degree of freedom here is actually, okay, so in the previous scenario you were actually having a pair, right? To actually find the value of the critical value from the table. Here you will get the degree of freedom as c minus 1 comma c minus 1 multiplied by r minus 1, right? That's actually from the table, right? Firstly you have c columns, number of columns minus 1 multiplied by and then the second value is actually c minus 1 into r minus 1, right? Now you have f row is actually ms between rows by ms residuals, right? So the degree of freedom here is okay, so this was for the columns, right? That is how will you find the particular say statistics critical value from the table. For the columns you will have c minus 1 into c comma c minus 1 into r minus 1, and for the rows you have r minus 1 comma c minus 1 into r minus 1. Same thing here, but r minus 1 here, right? Okay, so now it calculated the f value. If a calculated f value is greater than f value from the table, right, then you will actually do what is actually reject, right? Means if as always, means if the value calculated, whatever you have calculated is coming out to say greater than the value from the table, whatever you are getting from table, you will actually just reject that. So you can actually draw it on this particular example, right? That is you have to do a two-way ANNOVA for this particular one. You can calculate multiple values according to this particular these particular formulas, right? And also from this particular table, right, you can actually do two-way ANNOVA and get to see by considering the two factors that whether you need to accept HOC and also to accept HOR or not, or whether you need to reject both of those by calculating the values according to the degree of freedom from this ANNOVA. Thank you so much.